And welcome Calculus 2 students once again. We are looking at alternating series. In this case we're looking at series that bump back and forth across the x-axis. Now in this alternating series test, what we're saying is that the values of our terms must be decreasing, meaning that the next one is going to be less than the previous one, and that's just the magnitude of it. So we don't care that it's bouncing back and forth, just as long as the magnitude of that a sub k is getting smaller and smaller. And it follows from this that, and what they're saying is that if the limit of these terms goes to 0, then we can say that this alternating series converges, and both of these two cases have to be true. If we look at what follows from that is the fact that the alternating harmonic series follows both of these, which then means that it is converging if it is bouncing back and forth across that x-axis, meaning that one of them's positive, one of them's negative, one of them's positive, one of them's negative. So with this first example, I see that this part tells me that it's alternating. If I look at this bottom part, I see that it is an alternating and then p series. And because of this, I can say that this thing then converges. So I need to say that the limit of my a sub k, or the limit of my 1 over k squared, equals 0 because it is a p series and p is greater than 2. It is alternating. So I have that it is alternating. The limit of this a sub k is 0, and my terms are non-increasing, so they are decreasing, so I can say that this thing converges. Now I need to come up with a way to write these. I see that it's alternating, so we can write that it is -1 to the k plus 1, and then I could write that these terms a sub k are, I'm just going to write this as 2 over 1 so that I could see it a little clearly. It looks like it is a k plus 1 over k. Okay, so this is what I've got. It's alternating, and I've got k equals 1 to infinity, so I can write it like this. This right here would be my a sub k. I am looking at this one and I'm trying, let's rewrite this a sub k as 1 plus 1 over k, and then we'll take the limit of this. And even though these terms decrease, this limit is not equal to 0, so I'm going to have to say that this one diverges. So limit as k goes to infinity of this a sub k, 1 plus 1 over k equals 1. So this thing diverges. Oh, we've got our little friend back again, but this is an alternating sequence. My a sub k is that natural log of k over k. If I can show that these terms decrease, I don't really know what they do, but if I can show that these terms decrease, which I believe they do because this thing is getting big smaller and this will be getting big faster, so I believe that they are decreasing. I need to show that. One way to show that is with the first derivative, and I could show it with that first derivative test. Let's just go ahead and do that. F of x equals natural log of k over k, and then if I take the derivative of this, I'll get, that's going to be, going to use the quotient rule, and using the quotient rule you'll end up with 1 minus the natural log of x over x squared. The places where this would be our critical points are going to be at let's see, x equals 0, and so at x equals 0, this thing is on the right hand side of this, which is where I need to look because I need those values that are greater than 2. So on the right hand side of this, I see that this derivative would then be negative, which means that, so f prime of x is negative if I plug in, say, a 1 or a 2 or something of that sort, which means that this thing is decreasing. And if this is decreasing, then all I need to show that is that the limit as k goes to infinity of natural log of k over k, if that thing equals 0, which of course it does, that means this thing converges. Alright, so let's look at this next theorem, and it has to do with the remainder and alternating series and what that remainder equals. We have a series that is convergent and alternating, and we do have that here. And they tell us that this is going to be the formula for this remainder. Note that this is the sum of the first n terms. So this is going to be s sub n. And then this guy right here, it's going to be r equals s minus s sub n, where that is the next term that comes after that. We know that r sub n is going to be equal to absolute value of the total sum minus s sub n, and that this has got to be less than or equal to a sub n plus 1 from this right here. Now this a sub n plus 1 is equal to 1 over n plus 1 from what we did here. And if we need to make sure that our remainder is less than 10 to the minus 6, now what we need to do is solve for n. And looking at this guy right here, I can say that n plus 1 has got to be greater than or equal to 10 to the 6, just flipping both sides. And in other words, in order to make sure that we have a remainder less than 10 to the negative 6, our n has got to be greater than, whoops, I said equal, greater than, just do like this, ten to the 6 or 1 million terms. Okay. Alright, I just wrote down what this equals. This is the sum of the first 9 terms, so that's s sub n. I need to find r sub 9, which is going to be equal to the real sum minus s sub 9. And we know that this is going to be less than or equal to a sub 10. I know that a sub 10 is 1 over 10 factorial. And this is about equal to 2.8 times 10 to the minus 7. It's a real small number there. So that means that my maximum error is approximately 2.8 times 10 to the negative 7. And that's all for that one. There are times when our sequences are convergent, but we don't really know whether they're absolutely convergent or just conditionally convergent. So these two theorems let us know when to know whether something is absolutely convergent or just conditionally convergent. So let's look at this first sequence. I see that if I'm going to look at the absolute value of this thing here, which is what they have me do, I need to see if this converges, this absolute value. That means all I'm really looking at is this k equal 1 over k to the 1/2. So this is a p series with p equal to 1/2, and 1/2 is less than 1. So this does not converge absolutely. If our p-value had been greater than 1, we would have said that it converged absolutely, but it does not converge absolutely, but it still might converge conditionally. So because it is alternating, it might converge. So let's just look at the limit as k goes to infinity of 1 over square root of k. Now this value equals 0 because the terms of this sequence decrease. I can see that this particular part does converge, so I would say that this A part converges conditionally, because part of it will, one form of this sequence would converge but another wouldn't. Alright, let's look at this one. I'm going to look at this right here, and I'm going to find this limit as k equals 1 to infinity, and I'm looking at 1 over k to the 3/2. In this case, p is 3/2, which is greater than 1, so this one converges absolutely. So I'll do converges absolutely. And it is a decreasing sequence. I do need to state that. The next one we're going to look at this sign of k. Now when I look at this one and I put in values of 1, 2, 3, I'm going to have some positive and some negative. It's not really just going to go positive, negative, positive, negative. But I will have some positive values here and some negative values here. So I can't use the alternating series test because it just doesn't apply, but I do know that the absolute value of sine is less than 1, and I can use that fact to say that the sine k over k squared, the absolute value of this, equals absolute value of sine k, because k squared is always positive, and I know that this is less than or equal to 1 over k squared. Now with this, I can say that this is a p series, with p being equal to 2, which is greater than 1. So I could say that converges. And now if I use the comparison test for this, I will find that no matter what this is, it will converge. So this one is another converge absolutely. Alright, in the next one, if I'm going to look at the limit as k goes to infinity of k over k plus 1, I'm going to see that this goes to 1, therefore this thing diverges, and I don't really have to look at anything else. Once I find that it diverges, I'm done. That makes that nice. Our next slide gives a nice summary of all of the different tests, and you'll find that in your instructor notes. So I would definitely go through that, and I would have this sitting beside me, especially when I took my test having to do with these different tests, and maybe have an example of each. Alright, and that concludes section 9.6. If you guys have any questions, see me at the Collaborate.